This is my fourth presentation about the best methods for reducing ketones to secondary alcohols. In this video, I'll show you some examples of the enantioselective reduction of ketones by non-chiral boranes and a chiral catalyst. Although many ketones can be hydrogenated enantioselectively, as discussed in the first video of this series, some ketones contain functional groups which are not compatible with the common catalysts used for ketone hydrogenation. These are functional groups capable of forming strong bonds to the transition metals contained in these catalysts, and thereby of destroying them. Such groups include thiols and other sulfur-containing functional groups, and chelating groups such as diamines, amino alcohols, or aminomethyl imidazoles. If a given ketone contains such groups, reduction with a borane may be a better option than catalytic hydrogenation. Enantioselective reductions of ketones by boranes proceed by an entirely different mechanism than catalytic hydrogenations. Here, the borane is activated by forming a bond to the nucleophilic enantiomerically pure catalyst. The resulting borane catalyst adduct then transfers hydride to the ketone, ideally by simultaneously forming a bond to the oxygen atom of the carbonyl group. This second bond would provide for a closer contact between the chiral catalyst and the ketone, and thus for a higher enantioselectivity. In order to act as catalyst, the oxygen-catalyst bond in the resulting product must be sufficiently labile to react with the borane and thereby regenerate the original borane-catalyst complex. According to this mechanism, other compounds capable of forming stable adducts with boranes will usually interfere with the catalytic pathway and lower the attainable enantioselectivity. Similarly, strong Lewis acids will form a complex with a catalyst and thereby deactivate it. These are some of the reported catalysts for enantioselective ketone reductions. The catalysts in the upper row are mostly proline-derived amino alcohols, which were the first type of catalysts of this type of reduction discovered by Corey and co-workers in 1987. The second row shows some newer developments, including some transition metal-based catalysts. The main advantages of these borane reductions are their high chemoselectivity and the mild reaction conditions, what makes this strategy suitable for complex, multifunctional ketones. The reactions are also easier to perform than, for instance, catalytic hydrogenations, and no co-catalysts are usually required. Problematic could be the amount of inorganic waste generated and the need of a hydrolysis of the borate esters and aqueous workup to isolate the target alcohols. Most of the reported examples use large amounts of catalyst, typically around 10%, but that may be caused by the bias of the scientific literature toward academic research. It is mostly academic researchers who publish their work, not industrial chemists, and academics rarely optimize reactions to become economically viable. On the following slides, I'll show you some examples where the amount of catalyst could in fact be lowered significantly. Because most of these catalysts are expensive and cannot be readily recovered, catalyst loadings of 10% would make this strategy unsuitable for most non-academic applications. This is one of those academic examples with 10% of catalyst. Because the reaction was finished in only 10 minutes at room temperature, a lower catalyst loading would probably have been sufficient. The most interesting aspect of this example is the use of a readily available lactam as catalyst precursor. This precursor is reduced to the pyrrolidine and then converted into the catalytically active oxazoborolidine upon reaction with borane. These reactions seem to proceed much faster than the uncatalyzed reduction of the starting ketone by borane. In this example, a more recently discovered manganese-based catalyst was used to mediate the enantioselective reduction of the same acetophenone as in the previous example. Again, the reaction conditions were mild and the enantioselectivity quite high. This is an example of an enantioselective reduction of a base labile ketone with the aid of an oxazoborolidine. Here, the reaction conditions were optimized and the amount of catalyst could be lowered to 0.3% and the amount of borane to only 0.6 equivalents. Still, at 30 degrees Celsius, the reduction was complete after only 1 hour, despite the small amount of catalyst. Thus, most of the reported procedures with 10% of oxazoborolidine will probably also give good results with much less catalyst. As mentioned at the beginning, however, it is important to avoid both nucleophilic and electrophilic impurities, because these can poison the catalyst or open other non-enantioselective reaction pathways. The reduction of ketones by borohydrides is a very fast reaction, and few other functional groups will be reduced at a similar rate. Aldehydes will usually be reduced even faster than ketones, but most other reducible groups, such as nitriles, olefins or pyridines, react more slowly than aldehydes or ketones. Thus, the only critical aspect of this reaction is that additional Lewis acids or bases may interfere and lower the enantioselectivity of the reduction and should therefore be carefully removed from the starting material. Here are some further examples and also some additional catalysts, but many more examples have been reported. Instead of boranes, catalytic enantioselective reductions of ketones can also be accomplished with other reducing agents, for instance with silanes in combination with a chiral catalyst, with enzymes or with phosphite. For reductions by silanes, similar catalysts as those used for borane reductions seem to work, as do chiral Lewis acids, for instance complexes of zinc with enantiomerically pure diamines.